Today we are meeting for the last time for the course two-phase flow with phase change in conventional and miniature channels. We have discussed two-phase flow regimes in conventional channels, and we have discussed modeling of two-phase flow using different models: homogeneous model, separated flow model and drift flux model. We have discussed how to evaluate pressure gradients and then how to integrate the pressure gradient to get the pressure drop, mostly in conventional channels. In the numerical example, we also considered a channel of 2 millimeter diameter, which can be considered as a miniature channel. But there is some difference between the flow regimes in conventional channels and miniature channels and the methods to evaluate the pressure gradients and pressure drop. So, therefore, it merits a separate discussion. So, today we will discuss two-phase flow and pressure drop in miniature channels. We will further classify miniature channels into two categories: mini channels and micro channels. We will consider the size range of 10 micron to 1 millimeter hydraulic diameter, and we will divide it into two categories: micro channels. When we say micro channels, we will mean approximately 10 micron to 100 micron hydraulic diameter, and when we say mini channel, we will mean the hydraulic diameter ranging from 100 micron to 1 millimeter. There is a difference in the flow regimes observed and the hydrodynamic behavior in these two categories, mini channels and micro channels. So, let us consider two-phase flow regimes in mini channels, that is hydraulic diameter ranging from 100 micron to 1 millimeter. Researchers have done experiments and they have observed all major flow regimes except stratified flow. You remember the classification of miniature channels, in that confinement number is used or the bond number based criterion is used, and the criterion is based on the phenomenon that below a certain size stratified flow becomes impossible. The surface tension becomes so dominant over buoyancy that stratified flow becomes impossible. In mini channels, people have not observed stratified flow, but they have observed all other major flow regimes: bubbly flow, slug flow, churn flow, annular flow, etc. So, at low gas velocities or gas volumetric fluxes, we observe bubbly flow, which contains distinct and distorted bubbles which are non-spherical, and they are considerably smaller than the channel. When Jg increases, keeping Jl constant, which means that the white fraction increases, then the bubbles get crowded, and because of the crowding, it results in plug flow or slug flow. Some researchers have called it plug flow, while some others have called it slug flow, and there is a difference in nomenclature. If the Jg increases further, keeping Jl constant, then churn flow is observed, and some researchers have called it pseudo slug flow, some have called it churn flow, some have called it frothy slug flow. And there is another kind of churn flow which some researchers have called churn flow and some have called frothy slug annular flow. Then if Jg increases further, then slug annular flow is observed, and further increase of Jg results in annular flow. Here flow regimes observed by Triplett et al. Are shown. In the first figure A, we see bubbly flow. And here JL is equal to 6 meter per second and JG is equal to 0.396 meter per second, and in figure B, plug flow is shown. Here JL is less, but JG is also less. And then in figure C, churn flow is shown, and figure D shows a different kind of churn flow. Figure E shows slug annular flow. Here you see it is essentially annular flow, but there is a slight resemblance with slug flow, because there is a thinning of the vapor bubble, and if it had it thinned further, then it could have resulted in splitting of the bubble, and there would have been a liquid slug between the bubbles. But here it does not happen, and it remains like annular flow. So this is something between slug flow and annular flow, and it is named as slug annular flow. Then the last figure, F, shows annular flow, where there is liquid annulus near the walls. At the center of the channel there is vapor with, of course, entrained droplets. It has also been observed that flow regimes in mini channels and also micro channels are independent of the orientation, whether it is vertical flow or horizontal flow, whether it is inclined or not inclined, or whatever is the angle of the inclination. Depending on the mass fluxes and volumetric fluxes of the liquid and vapor phases, there are different flow regimes observed, but for the same conditions, if the orientation is changed, then the flow regime does not change. And this is understandable, because in such small channels the effect of gravity is not dominant, and therefore whether it is vertical or horizontal or inclined should not change the flow regime. So there is a flow regime map, and actually different researchers have given different flow regime maps, and here a comparison of these flow regime maps is shown, and experimental data of different researchers are also shown. So there is bubbly flow, plug flow, and there is pseudo slug flow, and dispersed flow, slug flow, and annular flow. Different kinds of flow regimes are there, and there are transition lines between the flow regimes. There is a difference between flow regime maps obtained by different researchers, but there is similarity also. Now, how to calculate pressure gradient and pressure drop in mini channels? So, for that there are correlations for White fraction, and Mishima and Hibiki gave a correlation in 1996 for drift flux model, which we have mentioned before, and it gives C naught equal to 1.2 plus 0.510 e raised to minus 0.692 dH, and Vgj is equal to 0, and here the hydraulic diameter is in millimeter. Vgj has been taken as 0 because in mini channels it is observed that there is very small slip between the phases. So, the effect of local slip on the White fraction is negligible, and we know that Vgj is the gas drift velocity, and it represents the local slip between the phases, and therefore Vgj is taken as 0, and C naught is evaluated from this expression. Then there are other correlations given by different researchers. One gave alpha is equal to 0.8 beta, linear relation between alpha and beta, and the other gave alpha equal to C1 beta raised to 0.5 upon 1 minus C2 beta raised to 0.5. So, this is a nonlinear relation, and the constants C1 and C2 are also sensitive to channel size, and the same researcher has done experiments on different channel sizes and has given different values of C1 and C2 for different channel sizes. So, in many channels we see that different researchers have given different flow regime maps and different correlations for the white fraction, and even the same researcher has given different correlations for different channel sizes. So, now consider flow regimes in microchannels, that is the hydraulic diameter ranging from 10 micron to 100 micron. Experiments on 100 micron diameter tube. In these experiments, the following flow regimes were observed: bubbly flow, slug flow, and there are new flow regimes which are not observed in conventional channels and even in mini channels. These are liquid ring flow and liquid lump flow, and then droplet flow regime was also observed. Then experiments were done on 25 micron. This is 25 micron diameter tube, and in this the following flow regimes were observed: bubbly flow, slug flow, liquid ring flow, and liquid lump flow. Here the flow regimes are shown. So, there is bubbly flow, in which there are small bubbles, and then there is slug flow, and it contains liquid droplets also. Then there is liquid ring flow, in which there is a ring of liquid. Then there is a liquid lump flow and droplet flow. The same researcher did experiments on 25 micron diameter tube and observed these flow patterns: bubbly flow, slug flow, liquid ring flow, and liquid lump flow. Other researchers have also done experiments and they have observed different flow regimes. There is no common agreement between different researchers in case of microchannels, and different researchers have observed different flow regimes and they have given different correlations. So, one correlation for white fraction given by Serizawa et al. Is for bubbly flow and slug flow regimes, and it is a linear relation between alpha and beta. Alpha is equal to 0.833 beta. And of course, Vgj is equal to 0. Okay. So far, while evaluating pressure drop, we have assumed the properties to be constant, so that we can integrate the expressions easily. We integrated the expressions for the pressure gradients to obtain pressure drops due to friction, acceleration, and gravity, and there we assumed the properties like Vg, Vfg, Hf, etc. All these properties we have assumed to be constant. And also, when we did the energy balance, we assumed that the vapor generation is only due to heating. So, we did a simple energy balance, and then if there is a uniform heat flux, then we get a linear quality profile dx by dz is equal to constant, and if the heat flux is 0, that is a adiabatic channel, then we get a constant quality x equal to constant. If the pressure drop is small compared to the system pressure, then properties at the inlet and outlet pressures are not quite different. Suppose consider the example 3 in which the pressure is 10 megapascal. So, we have taken all properties at 10 megapascal. Suppose the pressure drop is 50 kilopascal. So, 10 megapascal is 10,000 megapascal. Suppose that is the outlet pressure, then the inlet pressure will be 10,050 kilopascal. And if we evaluate properties at 10,000 kilopascal and 10,050 kilopascal, we will get almost the same values. You can check from steam tables or from the program steamtap.exe. So, it does not matter at which pressure we evaluate the properties. It can be anything between 10 megapascal and 10,000 kilopascal and 10,050 kilopascal. So, we can evaluate the property at an average pressure called system pressure, and then we can use those properties and treat them as constant. That will not result in much error. And another thing is that the vapor generation is only due to heating, and we can evaluate it by simple energy balance as we have done in the numerical examples. So, if the heat flux is uniform, then dx by dz is equal to constant, and if heat flux is 0, then x is equal to constant, and we have used it in our derivations and numerical examples. But if there is a significant pressure drop, then what happens? So, in case of miniature channels, since the hydraulic diameter is small, the pressure gradients are large, especially the frictional pressure gradient is large because the hydraulic diameter is small. Also, because of change in quality, significant quality, there is a significant pressure drop due to acceleration also. And another thing is that in miniature channels, usually it is not possible to use very high pressures. So, suppose for common applications, the system pressure is not very high. So, suppose the pressure at the outlet is 100 kilopascal, nearly atmospheric pressure, and the pressure drop is 50 kilopascal, then the inlet pressure will be 150 kilopascal. Now, if we evaluate properties at 100 kilopascal and 150 kilopascal, we will see that there is significant difference between the properties, and in the pressure gradient we have these properties Vf, Vg, Vfg, etc. And these properties, when we evaluate along the length for different values of z, we will get different values, and therefore pressure gradient at every z has to be evaluated using the local properties, that is the properties at the local pressure, and then only can we hope to get an accurate value. So, if we treat properties as constant, so if the pressure drop is not small compared to the system pressure, then properties need to be evaluated at the local pressure for every axial location. So, properties vary with z, and we cannot treat them as constant while integrating the pressure gradient, and therefore we cannot integrate the pressure gradient by hand, and then it becomes necessary to do numerical computation by writing a computer code. Another complication is that vapor generation is not only due to heating but also due to flashing. You know from basic thermodynamics that when the pressure of a liquid vapor mixture is decreased, then the saturation temperature also decreases, and because of that some liquid gets evaporated and there is vapor generation due to that. Even if there is no heating, the quality will increase. So, the vapor generation is due to heating as well as due to flashing, and this should be taken into account in the energy balance. So, if we consider the vapor generation due to flashing in the energy balance, then we get this equation: dx by dz is equal to 1 upon hfg q double prime ph upon Ga. Here pH is the heated perimeter, and minus dHf by dP into dP by dz. So, this first term is the term which we have considered before. This is vapor generation due to heating, and the second term is the vapor generation due to flashing. If the pressure gradient is large, from here we can see that if dP by dz is large, then the second term will be significant and cannot be ignored. Another thing to be noted is that dP by dz is unknown. We are usually trying to evaluate the pressure gradient, and then we have to integrate it to evaluate the pressure drop. So, this is an unknown term, and it has to be taken to the left hand side and combined with the other terms containing the pressure gradient dP by dz. And then finally, we have to express dP by dz in terms of other quantities, and then we have to integrate and find the pressure drop delta P. And as mentioned before, we will have to write a computer code and do numerical computation to find the pressure drop. So, because there is vapor generation due to heating as well as due to flashing, uniform heat flux does not necessarily imply a linear quality profile. Previously, we have assumed a linear quality profile, but if this effect is significant, then we cannot assume it. And even if there is no heat flux, even if the channel is adiabatic, there will be change in quality, there will be increase in quality due to flashing. Okay. So, now let us consider some numerical examples. In the example 1, we have the same data as before, except that the length here is 5 centimeter, and we have to find the pressure drop in the pipe using homogeneous model, separated flow model, and drift flux model. The properties are same as before. Dx by dz, here we will calculate from the simple energy balance as we have done before, otherwise it cannot be solved by hand. So, this is the same calculation as before, 1.772 per meter, and the outlet quality is 0.0886. And dVg by dP is of the order of 10 raised to minus 5. So, m square is of the order of 10 raised to minus 3, which is much less than 1. So, it can be neglected. So, now first we use the homogeneous model. Mu bar is calculated as 95.7 into 10 raised to minus 6 Pascal per second, and the two phase Reynolds number is calculated as 522. So, it is laminar flow, and the friction factor is calculated from the laminar flow relation, and it is 0.0306. So, the frictional pressure drop is calculated from this expression, and this is the same expression as we have used before, assuming constant properties and linear quality profile. So, delta Pf is equal to 0.064 kilopascal, and pressure drop due to acceleration is g square Vf, Vfg by Vf xo, and it is equal to 1.5 kilopascal. Delta Pz is 0 because the channel is horizontal, and then by adding these pressure drops we get the total pressure drop as 1.564 kilopascal. Now we use the separated flow model for the same problem. REFO is calculated as 176, so it is laminar flow, and FFO is 16 by RE equal to 0.0905, and the average two-phase multiplier phi FO square bar is found from the Martinelli-Nelson graphs, approximately equal to 30, and R2 is also found from the Martinelli-Nelson graph, and it is approximately 25. Delta PF is equal to 2 FFO L by D G square VF phi FO square bar, and it is 5.66 kilopascal. Delta PA is equal to G square VF R2, and it is 0.26 kilopascal. Delta Pz is equal to 0 because the channel is horizontal, and then we add these pressure drops and get the total pressure drop as 5.92 kilopascal. Finally, we use the drift flux model for the same pressure drop. The mu bar is the same, then RETP is 522, so we get FTP equal to 0.0306, and alpha O is calculated using the drift flux model, and with drift flux model we have used the Mishima and Hibiki correlation. This correlation has been used. C naught has been obtained from this correlation, and VGJ is taken as 0, and then using this C naught and VGJ we have evaluated alpha corresponding to the outlet quality. So it is alpha O. So alpha O is equal to 0.637, and using this value of alpha O we calculate R2 from this expression, and we get R2 equal to 21.3. The frictional pressure drop delta PF is calculated from the homogeneous model, and it is 0.064 kilopascal. The acceleration pressure drop is equal to G square VF R2, and R2 we have calculated, so we get delta PA equal to 0.222 kilopascal, and delta PZ is equal to 0 because the channel is horizontal, and then we add these three pressure drops and get the total pressure drop as 0.286 kilopascal. As I have mentioned for previous examples, here also these examples are given only for illustration, to illustrate the methods and application of the methods, and because the calculations, a lot of calculations are involved, there can be errors in calculations. So please do your own calculations and check. So with this, the course comes to an end, and we are going to have a live session, and in that we can discuss doubts, and hopefully we will meet again in another course. So thank you very much and goodbye.